In the last lecture, we derived a relationship for first law of thermodynamics that can be applied for open system, for an open system. So, if you recall the expression, that is dE by dt plus m dot I m dot E h E plus V E square by 2 plus G Z E minus m dot I h I plus V I square G Z I is equal to Q dot minus W dot. So, if you look at this, this is basically unsteady term, and which indicates how much energy being accumulated in the system, right, and per unit particular time, it is basically unsteady term. And this is your enthalpy, and this term is, if you look at kinetic energy term, and this is your potential energy term, and similarly at the inlet this is about exit, right, and this is about inlet, the enthalpy, kinetic energy and potential energy, and this is your heat interactions, right, and this is your work interactions. And not only that, we need to look at this equation for energy conservation, but also we need to look at mass conservation equation, which we have derived as dm by dt is equal to m dot I minus m dot E. That means, the mass being accumulated is equal to mass in being entering into the control volume minus mass of the going out. Now, what we will be doing this, we will be applying this energy equation, also the mass conservation equation for open systems, and take some examples and then look at it and how we can apply, what are the assumption we will be making, and how we can simplify the problems, those things we will be looking at. For that, let us consider a steady flow process, right, and if it is a steady flow process, then we can simplify this equation. Question arises whether any engineering device is there which we can consider as a steady. Steady means nothing is changing with respect to time. Is it we can think of? Because if you look at, like, let us say the fan is running, right. If a fan which we use in our in summer season, ceiling fan we use, right. So, that is almost remaining constant, moving at the same RPM, right, if there is no change in what you call voltage, input voltage to the motor, right. The flow will be coming in, that will be almost constant, you can assume, right. Yes or no? That we can. There are several like systems in engineering which we can assume very happily to be operated at steady condition. For example, power plant, you might be knowing that Kanpur city is having a power plant, yes or no, that is your steam power plant. Let us say power plant will be operating almost at a steady state. Similarly, your heat exchangers and other things, several devices we can assume to be what you call remaining almost same conditions for months together, unless it is the system is shut down for maintenance. You might have heard a lot of noise sometimes from our power plant which is located in Panki. Am I right? Did we hear? Lot of noise will be coming continuous manner, that is basically shutting down of the systems kind of things, right. So, therefore, these devices like we can analyze it by assuming the flow to be steady, very. So, let us consider a gas turbine engine, which is quite complex. It is having what you call compressors, it is having what you call combustion chamber. There are various kinds of compressor here, like low pressure compressor, high pressure compressor, and you may have take out the air, and there is a combustion chamber, the turbine and the other things. So, if you look at this very big gas turbine engine, which can give you something power of 55.2 megawatt, and it is rotated at 36,000 RPM with of course, the steam injections, and length is 6.2 meter, it is a very huge, and weight of course is 12.5 ton kind of thing. Now, when we apply this kind of energy equation, like we have looked at kinetic energy term. Now, let us look at if the kinetic energy term, if the velocity change, whether we can neglect or not, right. Velocity, kinetic energy term, velocity goes by square. If the change is a low velocity, there is a change, that change will be negligible small, but whereas the higher it will be. For example, like if V1, 0 and V2 is 45 meter per second, and if I take the change in kinetic energy terms, right, that is of course the specific energy, that will be what? V2 square minus V1 square divided by 2, that will happens to be 1 kilojoule per kg, right. This is your change in kinetic energy, specific kinetic energy per unit mass, But if you look at the change is 45 meter per second, but if I go for 500 to 502 and the same amount of energy 1 kilojoule per kg, there is only 2 meter per second, but there is a huge. So, one has to be very cautiously, neglect this term, right, because keep in mind that at high velocity, even a small changes velocity in velocities can cause a significant change in kinetic energy of the fluid. So, we will be also making lot of assumption how, where, when we can neglect the potential energy term, change in potential energy, and the work done by the system, and then heat interactions also we will be doing that. Let us consider a steady flow process. As I told that most of engineering devices such as diffusers, compressors, turbine, pumps, etc., operate under steady state conditions, right. We can assume that without much. So, for that what we will be doing, we will be saying that dm dt is equal to 0. Steady state means, like there will not be any change, accumulation of mass, it will be coming and going. So, that, and then the mass flow rate at the exit is equal to the mass flow rate at the inlet, whatever is entering, is going out at the, and this is equal to m dot. And in this problem, particularly diffuser and the nozzle, we can say there is no work done, right. But whereas for the compression and turbine, we cannot say this is constant, okay, right. And heat interaction, we can say it is what you call constant. Let us say that first law of thermodynamics for a steady flow process, what it will be, m dot T into this term, that is your energy, total energy, minus the at the inlet total energy is equal to q dot minus W, because in this case if you look at dE by dt is equal to 0. So, therefore, we are not considering the unsteady terms for the steady flow. And since this m dot I is equal to m dot E dot is equal to m dot, that is from the mass conservation steady for the steady flow. So, then we can divide this, I can divide it by m dot here, m dot here, and m dot here, and m dot here. So, what I will get? I will get a expression H e minus H I have taken over this, this term, and there is a change in the kinetic energy, right, and this term is nothing but your change in kinetic energy, and this term is basically change in potential energy, and this, keep in mind, specific potential energy, this is specific kinetic energy, and this is specific enthalpy change, specific enthalpy change, and is equal to, this is specific like heat and then work, this is basically heat and this is specific heat and this is specific work done. So, if I consider that some problem where the change in kinetic energy is 0, that means this term will be 0, and change in potential energy will be 0, this term will be 0. So, then what will get? You will get an expression that is equal to H e minus H I is equal to Q minus W, right. Are you getting? So, this term you will be getting. Is it similar to that your first law of thermodynamics for control mass system? Yes or no? This is nothing but I can write down, I can write down that this is basically, you can write down as d h is equal to d q minus d w. Yes or no? I mean, this equation is similar to that, right? But the first law of thermodynamics for a control mass system, right, what is that? That is du is equal to dq minus dw. It is almost similar, right? It is not same. Only thing is that here it is internal energy, this is your internal energy change, and this is your enthalpy change, and that same is a heat and work kind of thing. So, you can think of using that. Are you getting? Right? Of course, this is for a unit mass, and this also you can write down as a unit mass. I can say this is basically for unit mass will be du is equal to dq minus dw, right. So, you should keep this in mind that for a steady flow process, the what you call the energy equation or the first law of thermodynamics is similar to that of the for the what you call control mass system, except that only the internal energy in the control mass system is replaced by the change in enthalpy, that is all. Okay. So, now we will apply this equation rather for some application. Let me tell you, we are going to take an example where we need to consider the original equation, right. I will just tell you that. So, let us consider the diffuser and nozzles used in your nozzles do use in your garden hoses and jet engines, rockets, spacecrafts, wind tunnel, several places nozzles and diffusers are being used, right. You might have played with your what you call garden hoses, right. Yes or no? Because there like suppose you want to send the water to a little away from the place, what you will have to do, right. Suppose you are putting water here in this and then you want to send to another 1 meter, let us say, what you will have to do in the hose pipe? You will have to block the the nozzle exit, yes or no. So, that what will happen? You will, when you block, the area will be decreasing, and then so that your velocity will increase, right. So, let us consider a case of a nozzle. What you do, like if the fluid is entering with a certain velocity, let us say V1, this is your station 1 we are considering, and station 2 here, and the fluid is entering with a certain velocity V1, and then when it moves through the nozzle, because there is a change in area, area is higher at the station 1 and then it is low here, if you look at, this is your area, cross sectional area, then what happens, the velocity has increased. As I told, that area is decreasing at the exit of the nozzle, therefore, velocity will increase. Why it is so? Because we know from the what? From the continuity equation, yes or no? Okay, we will discuss that. And then similarly, for the diffuser, the fluid will be entering into the diffuser at a very high velocity, and then the velocity will decrease because the cross sectional area has increased here. If you look at, this is your cross sectional area, right, and you can take this as a control volume, the kind of thing, dashed line. This is your basically control surface, you can say, right. Now, we want to analyze what is happening. I want to find out, let us say we will take a nozzle, what will be the velocity, exit velocity, if I know the inlet velocity. Similarly, in the diffuser, and then for that we will have to apply the what you call mass conservation equation and then energy equation. But what assumption we can do? Already we have made one assumption, that is the heat is what you call transfer during this process, when it is the fluid is moving through the nozzle, is 0. Why? Because the velocity will be very high, and so that the residence time will be very low to have this heat transfer to take place, and we can assume similarly. And is there any work done by this? Because there is no shaft work, right. So, the work done will be 0, right. So, also the heat interaction will be 0, and the change in the potential energy, if you look at, because the elevation is almost similar nature. So, we can say that the change in potential energy is 0, and for the steady flow process, we have seen that apply this what you call mass conservation equation, dm by dt is nothing but your m dot 1 in this case minus m dot 2, this is equal to 0. So, therefore, m dot 1 is equal to m dot 2 is equal to m dot, right. And what is that m mass? If you consider, that is nothing but your mass flow rate, that will be mass flow rate. If I consider 1 is equal to rho 1 A 1 V 1, right. That means rho 1 is the density, A 1 is the cross sectional area. If I consider this is the cross sectional area, this is nothing but your A 1, and this area is A 2, right. So, is equal to rho 2 A 2 V 2. If I consider the density is same, not changing, so what will happen? This can be cancel it out, right. If I am assuming rho 1 is equal to rho 2. So, therefore, I can write down A 1 V 1 is equal to A 2 V 2. If there is a decrease in the area, A 2 is decreased. So, what will happen? Then V 2 will what will happen? Increase. If A 1 A 2 is decreasing, V 2 will increase. So, therefore, you are getting higher velocity in case of a nozzle and diffuser just opposite. Okay. So, now whether if you look at assumption wise, we have assumed that change in potential energy is 0. Can I say change in kinetic energy 0? I cannot afford to, because we are either increasing velocity or decreasing the velocity. So, that we want to know. So, therefore, and also it will be very higher, right. So, we cannot really this thing, and then we will apply the first law of thermodynamics, and what you will be getting? We will be getting enthalpy at the station 2 plus the V 2 square divided by 2 is equal to H 1 plus V 1 square divided by 2. How we are getting this? Any idea? Right? We have already seen that if you look at equation wise, and this is a steady flow process. So, therefore, in this case it will be 2 S 2 plus B 2 square by 2 plus Z Z 2 minus M I M 1 here, 1 here into H 1 plus V 1 square by 2 plus Z Z 1 is equal to Q minus W. So, this is 0, this is 0, and this is neglected. So, then what will get? You will get this expression, that is, and m naught, if I can divide this is equal to, I can write down S 2 plus V 2 square by 2 is equal to H 1 plus V 1 square by 2. So, this is the expression we can get, and we got that thing, right. So, and so that we can write down this basically equal to V 2 square minus V 1 square is equal to 2 H 1 minus S 2. So, therefore, we can say that this is basically, if I say this V 1 is very, very small, it is 0. So, V 2 is equal to root over 2 H 1 minus S 2. And for an ideal gas, like what we can write down is V 2 is equal to root over 2 Cp T 1 minus T 2, right, for the ideal gas we can say. So, the above equation becomes that is V 2 is equal to root over 2 Cp and T 1. I can take a bracket in the 1 minus T 2 by T 1, and if I assume the flow to be isentropic, right, then I can relate this temperature T 2 by T 1 with respect to pressure by using the isentropic relationship, that is T 2 by T 1 is equal to P 2 by P 1 power to the gamma minus 1 divided by gamma. So, that I can put it here and do that, and in this case, if you consider that it can be considered as an isentropic, provided you assume there is no friction, on the wall, right, which is very unlikely, but however we use this thing for the isentropic, considering isentropic flow for the analysis because of simplification, and already we have assumed that heat loss from the system is 0, right. So, now we will take an example like to how to compute and how to use this equation. Let us say hot gas from a combustor at 0.5 megapascal, like, and 800 Kelvin enters into an adiabatic nozzle. Adiabatic nozzle means there is no heat transfer from that nozzle, we are saying, with a velocity of 25 meter per second, right, and gets expanded to 0.1 megapascals, basically atmospheric pressure. Determine the temperature and velocity of gas at the nozzle exit, assuming no losses during this expansion process, and of course, we can take a molecular weight of gas as 18 kg per kilomole. So, if you look at what are the given is the P 1. So, if you consider the nozzle, let us say this is a nozzle where fluid is entering and leaving at a very high velocities, and this V1 station 1 and V1 is 25 meter per second, and if you look at this is basically P1 is 0.5 megapascal and T1 is 800 Kelvin, and this P2, this is your station 2, P2 is 0.1 megapascal, and I need to find out T2 and I need to find out V2, right. So, this has to be found out. So, what we will do, we will have to apply the what you call the relationship what derived just now, and we are assuming the flow to be what you call isentropic, because it is already given, there is no losses, right, and also given as the adiabatic, that means this thing is 0, right. So, therefore, we can assume to be isentropic. For isentropic flow, we know T2 is equal to T1 P2 by P1, and P2 is given to you. What is that? That is 0.5 megapascal, P1 is given. So, that is your 0.1 and T1 is given, that is also, and then gamma is given. So, you just substitute those values and find out that you find that it happens to be 611.8 Kelvin. It is reduced, right. And we can now find out the velocity. We will find out V2 root over V2 is equal to root over 2 Cp T1 minus T2 plus V1 square. Keep in mind that we had neglected in the last derivation that V1 is small or 0. So, therefore, but here we have retained it. So, that from the energy equation we can get, and you can but now question is how to evaluate this 2 Cp, and we are saying this is an ideal gas, that is an assumption we are making, and from that we are finding out Cp is equal to gamma r divided by gamma minus 1. Gamma is given, and then we know this r is basically specific gas constant, that is Ru, Ru is given here, Ru, and molecular weight, right, and you just substitute this value, you get 2.77 kilojoule per kg Kelvin, and then you put this all the values here, 2 into Cp value is 2.77, and the T1 is 800 Kelvin, T2 is 611.8, and 225 meter per second as V1, you will get 1021.39 meter per second. Suppose I will assume that there is not much effect of this inlet velocity, which is 25 meter per second, because the exit velocity is 1021.39 meter per second, which is quite what you call high as compared to the inlet velocity, right. So, if I assume that to be neglected, then what kind of error I will make, that you take is you can calculate that, find out that error will not be much, number 1. Number 2 is that if you look at velocity is very high, right. Now, we have consider that the flow, I did not mention that when we talk about the density at the inlet and the exit is same, I have assumed when we are talking about mass conservation equation, right. Yes or no? But actually here the velocity is very high, right. Whether it will be, I can assume this density at the inlet and exit of a nozzle to be same, provided it is incompressible fluid. If it is compressible fluid, then we cannot. Okay. Are you getting my point? Now, how we will know whether it is a compressible fluid or not? For that you need to of course go for compressible factor, from that you can find out the speed of sound, right, and then you will have to find out Mach number, like Mach number if you look at, if I say this Mach number is equal to V by A is the speed of sound, right, and if Mach number is very very low, then we call it as an incompressible fluid around 0.2, you know, like kind of things. Then only we can, you know, say that density at station 1 and is equal to the density at station 2. That means, when m is, you know, less than equal to 0.2, right, I can say that rho 1 is equal to rho 2 because incompressible fluid, right. Fluid. But if it is more than that, it is a compressible fluid where you cannot assume that rho 1 is equal to rho 2, you will have to take care of the density factor, right. So, you know, that depends upon the, if you look at, we have taken very simple example, complexity of the problem also increases as you go on and kind of things. So, let us look at how we will handle the gas turbine, you know, like if you look at turbines, there are several kinds, gas turbine, steam turbine, hydraulic turbine, wind turbine, you know, like where we generate power, and power is very important, you know, like particularly in modern life to have a comfortable life, you know. So, therefore, but what is the turbine? Turbine is basically a wheeling device that produces short power when working fluid is passing through it. As I told that, you know, like a turbine will be having several blades, rotating blades, stationary blades, and it should be designed properly, you know, so that you can extract the work from the fluid, which will be, you know, at inlet of, let us say, entering with P I, V I and T I and leaving with P E, V E and T E, and then that power has to transfer to the shaft, and then you can utilize that power, mechanical power. Basically, we are getting the what you call thermal power is converted into mechanical power here, and you know, like we will be also trying to handle the compressors. There are various kinds of compressors are there, you know, like, okay, what is a compressor? Compressor is basically where you will be compressing the fluid so that its pressure will increase, right. So, if you look at your ceiling fan or the table fan, whatever we use in summer, can you call it as a compressor? Similarly, let us say, you know, like there will be a blower, you might have seen in your hostel, it is there, if you go to your kitchen, you know, there is a blower, right, you have seen that. So, if you have not seen, you just see, there is on the top there will be a blower which will be to suck out the hot gases and other things. So, compressor there, and there is a pump also. Whenever we use liquid, we call it as a basically the what you call a pump. Now, the compressor, if you look at, is a pressure what you call, it is a pressure producing device by absorbing the work. In the turbine, in case of a turbine, the turbine will be producing the work. Okay. In this case, this will be consuming work and then producing the pressure. There the pressure you know, will be what you call energy will be used to the produce the work. And as I told, there will be a fan, blower, compressor, pump, there are several kinds. We use left and right in industrial applications. So, the schematic looks like that, it is having rotating blades and stationary blades not shown in this figure, and it is, you know, like where pressure, exit pressure is greater than the inlet pressure, right, exit pressure is greater than the inlet pressure. And in the turbine, it is other way around, exit pressure will be lower than the inlet pressure. So, how to handle these problems, that we will see. So, what are the assumption we will be making? We will be making this compressor or the turbine, you know, any one of them, like is operated under steady state condition. That means the steady flow, if it is a steady flow, then by applying the mass conservation equation, we can say the mass flow rate at the inlet or the one station is equal to the mass flow rate at the exit, at the station 2 is equal to the mass flow rate. And we are saying the change in kinetic energy and potential energy is 0, but not all the time. Okay? we are just making assumption, and there is a adiabatic system, no heat is going out, actually it will be dissipated during the either the compression work or the expansion work in a turbine, in a compressor and turbine respectively. So, first law of thermodynamics for a steady flow process, we have already seen this expression, right, we have seen. So, we can apply that. What we will do, we are basically saying this change in kinetic energy is 0. So, this is basically 0, potential energy is 0, right, and this is 0 because of adiabatic in nature, right. So, if you look at, then we can write it down as an expression m dot E H E minus H I, because we have seen m dot 1 is equal to m dot 2 is equal to m dot. Okay. So, and keep in mind that this I am using basically inlet and this is exit, okay, 1 and 2 corresponding to inlet and exit. So, therefore, it comes after work. So, this is a equation for what you call either compressor and turbine. Keep in mind that in some places we cannot afford to make this assumption what we have made. See, this assumption may not be valid, okay, that we will see an example and see that. And the what you call the shaft work is basically will be positive for a turbine, because it is done by the control volume, right, and work done what you call input to the compressor is negative, because it is you are giving externally to the control volume. So, therefore, that will be negative. And let us take an example that an adiabatic turbine in a steam power plant operating under the steady state condition received 5 kg per second superheated steam at 4 megapascal pressure and 573 Kelvin temperature, and the steam enters turbine with a velocity of 20 meter per second, which is a very low, at an elevation of 2 meter, right, and above the ground level, and the turbine discharges a wet steam of quality X is equal to 0.5 at 50 kilopascal pressure with a velocity of 70 meter per second at an elevation of 8 meter per second above the ground level. So, if you look at there is a what we call let us say this is your turbine, there is a blades, there is a shaft work and this is 0, and there is a inlet here, let us say, and from the elevation if I take, this is something z is equal to 2 meter at the inlet, this is my inlet, and there is a exit, and this is exit is what, z is equal to 8 meter. Okay. And this V exit is 70 meter per second, and V inlet, this is exit, V inlet is 20 meter per second. See, in our problem or in the derivation we have neglected that change in kinetic energy and change in potential energy and derived. But now here the data is given, we need not to neglect it, but we will have to see if we will neglect what will be the error, that is the being asked, how much error will be introduced if we will neglect this. So, these are the data I have already mentioned about it, and the P I is given 4 megapascal, T I 573 Kelvin and V I 20 meter per second, Z 1 is 2 meter per second, and other things like the steam entering at a x is equal to quality is 0.85, and we will have to find out the work done and percentage of error if we will neglect or the terms kinetic energy and potential energy. So, and for this turbine problem, we can apply the first law of thermodynamics considering it as a steady state, and we will invoke this first law of thermodynamics, which is consists of the total energy term including the flow work and the heat and the work interaction. So, what we will do, we will basically take the data and from the superheated steam table at pressure P I 4 megapascals and T I 571, and that will get the enthalpy as 2961 kilojoule per kg. And keep in mind that for the steady flow equation, we had neglected the kinetic energy and potential energy term, but here we are keeping the same. However, we will be what you call make it 0 this term because it is adiabatic turbine. So, let us then we will have to get the data from the saturated pressure steam table, that is the exit pressure of 50 kPa, and that is HF is 340.5 kilojoule per kg and HFG is 2305.4 kilojoule per kg. And we know the quality of the steam, which is at the exit of the turbine. So, that is 0.85. So, we can find out from this data, right, and this enthalpy data corresponding to 50 kilopascals, we can evaluate the enthalpy at the exit, that is HF into X, this is the quality, into enthalpy HFZ, and if you just substitute those values, we will get something 23,000.1 kilojoule per kg. Keep in mind that this enthalpy HE is between the HF and HFG because the quality is 0.85. That cross check one has to do while solving a problem. Sometimes you may make some mistake. And what we will do, we will basically substitute this HE and H what you call I, which is Hg is equal to Hi, and then what we will do, we will basically we know the velocity is given to you V exit, that is 70 meter per second, and the Z is given to you, that is something 8 meter, and Vi is given 20 meter per second and Zi is given 2 meter per second. Substitute those values here in equation 1, and then you can find out the shaft work as basically 328 through 3 kilowatt. If you look at this term is very low, this is corresponding to the kinetic energy, change in kinetic energy term, and this is corresponding to change in potential energy. Of course, this is your mass. Now, this is a quite a bit power being generated by this turbine. Now, we need to find out what will be the error if we will neglect the change in kinetic energy and change in potential energy is almost 0 kind of thing. So, for that power due to change in kinetic energy potential energy can be evaluated very easily, like taking this change in kinetic 2.25 and change in potential 0.059 into 5, it is coming around to 11.5 kilowatt, which is very small as compared to 3283 kilowatt. So, percentage of error if you calculate, you will get basically percentage error is equal to 11.5 divided by 3293 into 100, this amount to be something 0.35 percentage, which is negligibly small, right. And therefore, we always neglect this term, but however, if in your problem it is given that you will have to evaluate, please do that. Okay. So, I mean we have seen why we are neglecting the kinetic energy and potential change in a turbine or compressor problem, or any other problem also we can neglect provided it is a small quantity. We will discuss some other applications of the first law of thermodynamics in the next class.